So the second presentation will be about the measurement of see-through distortions, and this time we have two speakers. So the first speaker already on stage is Adrian Betanzos. He is a principal at VIA, which is a facade consulting firm. He also worked for Apple, Vitro, and Permas de Lisa. And in addition, he has been an adjunct professor and guest lecturer at multiple universities. And the second speaker is Louis Moreau. He's from Moglex Corp in Canada. And he has over 3 decades of expertise in the North American and European glass sector, and hence a lot of know-how in various fields, including glass melting, advanced coating, sputtering, large-scale building glazing, optical characteristics, and structural design and construction. He is also chairing an ASTM task group where they established a new standard method for evaluating anisotropics in architectural glass. So, yeah, the stage is yours.
She was taking the picture, so I was smiling for the picture. Yeah. Better? Thank you. You know, otherwise the pictures sometimes they get really ugly. Anyway. Anyway, I like to start the presentations with a hola, hello, bonjour, because we have to say hello, and that's a nice thing to do. In the next sort of 15-20 minutes, we want to talk about this topic of a see-through distortion. We want to show a little bit of the basics of how light goes through a transparent material. And we want to understand if there will be more people interested in this subject, which I think there are. It would show, the presentation is divided in two. That's why we have two presenters, Louis and myself. The first presentation is me, showing a little bit of the relationship that Louis and I have had for the last 10 years or so, which is I'll show up with problems, and then he will show up with solutions. And that's how we're presenting it today. I'm going to show you the problems, and then he will tell us how we're trying to fix it. Even though this topic is a little bit obvious about reflected and transmitted distortion, sometimes we've noticed that it's not that obvious for many people. One of the annoying parts is that they are not mutually exclusive. One can be there and the other cannot, or sometimes they can be together. So you don't really know what's happening. And today, the industry is only checking on the reflected distortion, not really doing anything for transmitted distortion. Here is a picture of a beautiful kid, which is mine. But what I'm trying to show is the image of the Brooklyn Bridge, how distorted that image is. It's a little bit unfair because it's on acrylic, and acrylic is a little bit not as flat as glass, but it shows you, the example of a reflected transmission. And the same on the other side, when you're looking through this acrylic or through the glass on the side, you see all the distortion of it. So that's the transmitted distortion. We're supposed to see, or we were led to believe that a little piece of glass or transparent material, you put it there and you see through and you will see the same thing with or without it, with maybe a difference in color. Like for example here, where you have the windows are closed and when the windows are open, the only difference is just the light. The light's a little bit different, but with that 3mm IGU that is so thin, nothing happens and you can see through very well. But that's not really how it happens today. Today, this is how light goes through a transparent element. And if the two walls of the transparent element are parallel, then we have a lateral displacement. The image, you have a shift in the image, but you don't get a distortion on the image. So similar to the lobster. There's no 4 eyes in this lobster, it's just one lobster. So that's a lateral displacement. You can see that the lobster doesn't change, but it's in a different position. Now, when the two surfaces of the transparent material are not parallel, then we have this thing called angular displacement. The light shifts and moves, but also gets distorted the image, and and the funny thing here is it gets worse with how far away the image is. Here's one example of a beautiful picture, because I took it, but this shows the reflectivity of these lamps onto the flat glass. It looks almost perfect. The reflectivity is beautiful. Now you zoom out a little bit of the image. You still see everything very perfect, but you zoom in again to the bottom left, and you see that the transmittal is not as perfect as the reflectance. Yeah, you're going to say, well, it's a 30-degree angle or a 45-degree angle, a 60-degree angle. It just doesn't matter. It's how people see it, it's how people walk by it. Similar situation here on these doors. The glass on the right, you see the reflection of the window, or the circular light, and it's beautiful. But the same glass, looking through the glass, is not that pretty. And you know, have another image on the other side as well. It's just very, very distorted. This is one of the worst glass I've ever seen. This is in Mexico City. It's at the airport. In transmittal, and in reflection, is horrible. It's just horrible. For example, you're supposed to be reflecting these little windows, but even here, on what's supposed to be a flat single pane of glass, is super bad. So you can see it both ways. Again, another example of a window in California, and this is a observation deck where people were supposed to go there, and pay money to see the view of the city, but it's quite distorted, and well, you're going to charge people to do that. You cannot do that. Now, another one in New York where it almost looks like it was done on purpose because it's so homogeneous badly that it just looks nice, but it's not. You see one side and see the other side, and then you see the typical answer from a contractor where it says, you know, this was inspected as per industry standards, which was true. Reviewing through the glass is not something that warrants rejection. It is not an industry-recognized way of assessing glass panels, which unfortunately is right. It's legally correct. Whether it's good or bad, that's a different thing, but it's right. And now this is the same image, the same glass from the outside. It is good. So this passed inspection because it's a good glass according to how it was being reflected or designed or fabricated, which is not humanly centric. And then these are just some of the possible causes of what happens or what causes this distortion. Just bad quality of the glass or the float glass, bad lamination, multiple interlayers, heat treatment, or polishing marks.
Thank you, Adrian. So I think the demonstration is pretty good in terms of what is the difference between a reflected distortion and a transmitted distortion. In the glass industry right now, you have hundreds of scanners at the end of tempering light that are measuring only the reflected reference. And there is no inference in the industry, in the architectural industry, about transmitted distortion. And in the first year, so I've been consultant for a couple of years, and I had 4 mandates where people were complaining about transmissive distortion. So what I've done is I've looked at in other industries to find out how do they treat that. And the first one that comes to mind is the automotive, because the windshield you have, all the windshield manufacturers in the world are 100% inspected for see-through distortion or transmissive distortion. And we also look at aeronautical and architectural, and we'll finish up with architectural. So, so I'm looking at the different standards. So in the automotive world, the ruling, it's a bizarre standard. It's made by United Nations. I didn't know they were doing standard. It's called the R43. But if you look the ISO 3538 or the ANSI Z26, they basically have the same thing. So I'm taking examples from the R43 because you can download it for free. It's a public document. So there's 2 things that they look at: the optical distortion, and that the way they evaluate it is they take a projector with a slide with little holes in it, and 9 meters away or 7 meters away, you have a screen where the dots goes, and you put the the windshield or whatever piece of glass you want to do into the path, and you come to the screen, and you have a little target that you put on each dot, and you can see if it falls within this, you're good. If it's outside there, it's a go no go thing. It allows you to find out how much distortion you have for each dots that are projected. And depending on your geometry, the size of that, the size of the dots, basically the standard deviation in automotive industry is 2 minutes of arc. So it means that the light will not deviate more than 2 minutes of arc. That's for a football that high. It's about 700 meters away. So it's pretty small. Secondary image separation, that's another thing for cars. When you drive at night, you look at another car incoming. You don't want to see two cars, you want to see only one. So that's one thing that they do, they check. And they have two means of doing it. That's the most common one, and like that. So you just look at a target. It can be either a hole and this. And when you have the secondary image, this thing should always be touching the outer ring. The other target is this should be contained in here. Again, the geometry makes the thing. And for double image, the allowed standard in the automotive is 15 minutes of arc, so much more. For the ones that are more sophisticated, that's another way to check the double image. Here you have a position of your double image so you can evaluate, have a value. It's not a go, no go. You have a value and you have an orientation. But in fact, so these are laboratory stuff. You need to be in the dark. You're only dealing with little dots. So what happened in real for in the industry is that they have automated that. And now that's basically what they do on finished windshield. They have a robot, and they analyze the horizontal and the vertical distortion for each windshield. And some of them have a human operator, other don't even have a human operator. So the machine decides what it wants to do. And your end result is a mapping. So you have the intensity, so you know your number of millidiopters on the scale, and you can see where are your hot points, and you can determine different zone for the driver, for the cameras, for everything. So that is really mastered in the automotive industry. They have the scanner. Isra is a market leader. Synergex in Montreal is another one. GlassTech make one also, the tempering furnace guys. But it's there, and the windshield are all inspected to the standards, relating to the other standard. Now, you have the military and the aircraft industry. They also have their own set of standards. That's something I discovered. But they have the same problem with distortion and angular deviation. But when the military aim at something 2 kilometers away, it shouldn't be there. It has to be there. So the eye contact is very, very important. So here you have 5 different standards, and I'm going to go through that rapidly. Basically, they pretty much work the same way. So the fundamental one is the 733, where it was initially done with photographic film. You would take an image of a grid without a windshield, and then superimpose the second image, and then on the picture you would you would measure with a measuring tape. You would measure the distance of the deviation and deduct the milliradian deviation of the ray. Later on, they came up with the same principle and changing, analyzing the vertical and the horizontal distortion using CDD detectors, but it's basically works on the same principle. So I will go through there. In the military, they also want to have binocular distortion, so they take the 801, but they make another measurement 64 millimeter beside it. So that's the 1181. This one I don't know exactly what, but it's another variation of the 733. And the final one, which is a bizarre one, so instead of having unit as milliradian, they take the worst one, they put a tangent to it, and then they measure just the ratio of the height on that. So it's 1:5. It's 1 unit of measure, but Boeing still use that. So there's a company in Croatia that makes a software that does the thing automatically. So I took some of their slides, but you can see they have a big analysis software, and they relate to all the 5 standards that so you can measure the slope, you can have an output in milliradian and everything. But you see the kind of distortion that you can encounter in that. Now, in our world, in the architectural world, we have the C1036, which is basically done for float glass, but you can use that on a finished product also. I've done it many times. So here, what the observer is 9 meters away from a zebra board and looks through the piece of glass and rotate it until he sees the distortion. The setup is not easy because it takes a lot of space, and you have the zebra board has to be very big if you have a big piece, and then you have to manipulate and turn glass. So if you have big glass, it's not easy. But it works, and it gives a decent measure. Will depend on the operator and things like that, but it can work. And your output is the number of degrees you have rotated that. So it's just an output like that. So it doesn't relate to any physical units. The second way is the C1652. It's to photography a grid. So it's pretty much like in aeronautics, and it has been used mostly in reflective up to now. But I decided to try it in transmission, and it works very well. That's what I want to show you. So I don't know if some of you were, there was a presentation on what clipping does to laminates. So we did two laminates, and we clipped only one short side and one long side. Here, there's 2 laminates on top of each other, so I wanted to induce distortion, but we use stiff PVB, and we should have used other material to have a little bit more. So overall, the glass was not that bad. But anyway, we set it up. So you see our piece of glass here. We have our grid, which was a 25 by 25 grid. We also had a zebra board. And I was sitting here with my phone, just taking a picture of that. Then, that's the fun story. To analyze my picture, I needed the software, and I didn't want to recreate it. So the only piece of software I could find was a software called Inspector G. So Inspector G was a retirement project between Robert Maltby and Brinker, and Gary Brinker. And they decided to do a software to analyze the grids according to the 1652 ASTM. And that software has been available for many, many years. But the guys so Robert is 94, and his young associate is 84. So, but we managed, and I brought them at Synergex so they could look at the other technology, and the software will survive. So Synergex will take it over and will refresh it and everything. But so that's what I wanted to do. So this is the output of the analysis on the laminate you saw the clips. So you see that here on top there's a slight amount of distortion, but there's one side that is definitely have more distortion. And if you look at it, this is not a test, this is just to show you the difference between this side and this side, and you see very little here, but you see here there's something happening. So we did it with zebra. Here I'm at 60 degrees, which is already there. It's pretty good. The laminate is inverted, so now it's on the left. But So that's 60 degree, and that's 70 degree. So you see there's definitely a distortion band there, the same that was measured with inspector G. And what we did after that is that took the same glass, sent it to Montreal to be scanned on an automotive one, the same one you saw the robot. And that's the distortion that Synerjet came up with. So you have a long, very shallow, this long distortion on the top, and this band on the right. So the way those in the automotive, the way they analyze separately the vertical and horizontal. But you see there's a concordance, and even the number, even if it was a pretty good laminate, we had with this method 29 millidiopter of distortion. With the inspector G software, we found 23. So it's pretty similar. So there is a correlation, both visual, zebra, and automotive way, and analyzing the grid way also. So the next step, we think we want to push that further, maybe bring awareness to the industry that see-through distortion can be very disturbing. I had 2 projects where the whole facade had to be changed because of that, and it can be very costly. But we need to have a standard. We need to have a way to measure that is efficient, and that's what we propose. We want to see from you guys what you think. So we're here for the whole week, so you can talk to us and everything and find out that. Maybe you don't have a microphone anymore. Okay, so. Our objective is to create a measuring device and methodology precisely measuring the transmittal distortion. First at the factory, which is doable, we think, but also on site. So that would be the ultimate thing. Thank you.